So I think it's about time. Everybody, welcome to the afternoon session. This afternoon's session is sponsored by TNQ Publications, and the organizers and all the participants are very grateful for the support. So our first speaker this afternoon is Martin Bridson from Oxford University. Oh, and the Clay Math Institute, excuse me, who's going to tell us about profinite rigidity, Grothendieck pairs, and finiteness properties.
Karen, and thank you to all the organizers for inviting me and for organizing everything. It's a great pleasure to be in a country with 1 billion people who appreciate the beauty of cricket. So this talk and the following talk of Alan Reed are connected, and most of what I say, or a lot of what I say, is joint work with Alan Reed, and he and I have been pursuing this idea of Grothendieck rigidity for several years now, and other people are involved, and I'll mention them at the appropriate point. Now, I was conscious as I was preparing this talk that some of what I have is quite technical, but I'm going to try and distinguish what's technical, the details, from what's sort of important in the basic questions. And the basic questions and the statements of the main results are really very simple things, right? So interrupt me and ask questions if the questions, at least, and the main theorems don't make sense, because they really are sort of simple-minded in their statements. And above all, there's this statement, a very, very simple question. So to what extent is a group, and I'll come back to the adjectives in a minute, but to what extent is a group determined by its finite quotients, right? So you've got a group, and groups can be hard things to understand according to how they're described to you. And so you experiment with it, you explore it, you go out into the world and try and get it into action. And the most naive thing you can do is get it to act on finite sets. So look at linear representations, which is sort of captured by the finite quotients, as I'll try and explain later. And then you wonder how much of the group, or to what extent am I totally understanding the group? To what extent can you totally understand a group by understanding its finite manifestations, by understanding all of its actions on finite and linear spaces, or if you want, just understanding the finite quotients of the group. Now, the sort of groups I'm going to be interested in, so it's not so much of a restriction, they're all discrete groups. I'm going to be talking mostly about discrete groups, so that finitely generated groups, that is, the groups generated by a finite number of basic operations, or more, like most of the groups you come across in your everyday life, finitely presented groups. Right? But one of the themes here is there's a surprising difference, at least surprising to me, certainly not an obvious difference, between whether you would just assume your groups are finitely generated or whether you insist that your groups are finitely presented. You get very different answers to this fundamental question. Okay? And so I'm sort of interested in groups in general, but I'm most interested in the groups that appear in nature, as it were. So in particular, nature being low-dimensional geometry and topology, so it would be particular stress on the groups that you come across in low-dimensional geometry and topology. So, for example, the fundamental groups of 2- and 3-dimensional manifolds or orbifolds, and lattices and semi-simple Lie groups, things like that. Things one might think of as natural groups. The idea of profinite rigidity. So, what does profinite rigidity mean? Well, sort of the best answer to this question would be that in certain contexts, the group is completely determined by its finite quotients, right? So that would be an instance of profinite rigidity. Right? I'll explain the terminology a bit in a minute. But so something is rigid in the profinite sense if it's completely determined by its finite quotients, right? So, but there's actually some subtlety as to what you mean by that, and so through examples, I'll try and draw that out as to what we really mean by there's different forms of profinite rigidity. Now, if you're trying to completely characterize something, in any branch of mathematics, right? If you're trying to recognize something, you look for invariants, right? So you're looking for a complete list of invariants, perhaps, but you're certainly interested in invariants. So what invariants of the group, what properties of the group can you see by examining its finite quotients? That's what I mean by profinite invariants. And this idea of Grothendieck pairs will play a prominent role, but I'm not going to define it for you at the beginning. I'm going to try and let it emerge a bit. But a theme, so the main theme of the most recent part of this story, which is what Alan and I have been working hard on over the last couple of years, is the importance of finiteness properties, the difference in behavior between finitely generated and finitely presented groups in this setting. Okay? So those are the main themes. And sort of groups we're going to be interested in are things like this lovely group, and this is what I'm going to use as an example repeatedly. So we want groups that occur in nature. That's the 3-3-4 triangle group, the group of symmetries of that tessellation of the hyperbolic plane. And when I say the 3-3-4 triangle group, I'll usually mean this one, which is the group of orientation preserving isometries of the plane that preserve that tessellation, right? So that's got index 2 in this Coxeter group, this reflection group, which is generated by the reflections in the sides of a basic triangle. So when I write triangle 3-3-4, I mean the orientation preserving isometries of that tessellation. And that's an example, a natural example of a finitely presented group. Right? So the groups you come across in nature, if they're fundamental groups of compact manifolds or orbifolds or spaces, they'll be finitely presented. So a group which acts nicely on a space with compact quotient will always be finitely presented, like this. Right? So it's got 3 basic operations. So let's look at this one. X, Y, and Z, that's reflections in the sides of a basic triangle. And then you write down some rules which those generators satisfy. And then you stop if every other rule you can ever think of, every equation in the group, is a formal consequence of the ones you've written already. That's what it means to be finitely presented, right? You can completely describe the group. Right, now so we're trying to understand groups by their finite quotients. Now, sometimes this is going to not work for a very basic reason. It's a sad fact that there are lots of there's interesting groups that have no finite quotients at all, right? And if the group's got no finite quotients at all, then you're not going to find out anything very interesting by looking at its finite quotients. And so people might tell you existence theorems for these things, but they're not from a modern point of view, they're not so hard to find, and they're not huge things, right? So here's 2 groups, each with 4 generators and 4 relations, short relations. Those are 2 examples of infinite groups, so you have to work to see that those groups are infinite, but those are 2 infinite groups that have no finite images, right? So they have no actions at all on finite sets. They have no finite dimensional linear representations over any field. Okay? So such things exist, and so you have to account for that. And so when you're going to try and prove theorems about recovering a group or properties of the group from its finite images, you have to rule out things like that, because they're always going to cause you a problem. And there really are lots of such things. For example, something I proved a long time ago, you take any finitely presented group, you can always embed it in a larger group, controlling the geometry, make it a quasi-isometric embedding, so that the larger group is one of these such things that has no finite quotients at all. Right? So there's enough of these things, you can stick everything else inside it. On the other hand, sort of looking at images, there's an argument of Olshansky from the 1990s that every non-elementary hyperbolic group can be mapped onto an infinite finitely presented group that has no finite quotients, right? So you can embed anything in a group that has no finite quotients. You can map hyperbolic things onto groups that have no finite quotients. So you have to rule out that sort of behavior. It just exists. And just as an aside, so if you're staring at that for the first time and you think, how the hell do you tell those groups have no finite quotients? If you haven't figured it out yet, which, if you have figured it out, talk to me. That's very impressive. There's nothing algorithmic you could have done. You can actually prove there is no algorithm that, given a finite presentation, can work out whether the group has a finite image or not. Okay, so you need a theorem each time, but there's no algorithmic process you can follow. Okay, so to rule out such things, we really should be restricting our attention to residually finite groups. So to remind you, a group is residually finite if every element of the group every non-trivial element of the group survives in some finite quotient. Okay, so every element of the group survives in some finite quotient. And it follows easily from that every finite subset of the group can be injected into a finite quotient. So if a group is residually finite, then you have some hope of understanding the group from its finite images, because any finite chunk of the group can be injected into a finite quotient. Okay, so that's a setting in which you might really hope to understand the group by its finite images. And a lot of the groups, according to what you think nature is, a lot of the groups you come across in nature are residually finite. So all finitely generated linear groups are residually finite. And for example, all fundamental groups of 3 manifolds or orbifolds are residually finite. That's not a trivial fact. You need geometrization for that. And so the basic question we're really asking is, given if you've got a residually finite group, what can you tell about the group by understanding its set of finite homomorphic images, its set of finite quotients, or equivalently, all of its actions on finite sets? Okay, so has everyone got the question? There's nothing complicated about the question, right? We're just trying to understand groups by understanding their finite quotients. Now, here's something which, so it's like in mathematics, you all know there's objects that seem terribly complicated, and you use them every day of your life, and it's as if you learned them in kindergarten. And this is like one of those objects for me. But I also remember when I first came across this, I found it rather difficult to understand. And so I know from experience that you can't expect an audience to just take in exactly what this is, but it's still worth saying. So this is, when you're doing mathematics, you want to think of the right structures, right? So instead of taking all the finite quotients of a group and putting them all in a big bucket and examining them, there's actually a more intelligent way to organize them, right? They naturally form a directed system. If you've got one finite image of group and you map that finite image onto a smaller finite image, then that's sort of an arrow in some directed system, and you take the inverse limit of that directed system. So the profinite completion of the group is the inverse limit of that system of all of its finite quotients. Okay? So it's a sensible way of packaging up all of the finite images of a group. Now, if you take something like, even something easy like z, the integers, this is an uncountable group, z hat, right? So that doesn't necessarily seem like an intelligent thing to have done. You've traded a nice, easy, discrete group, z, for this uncountable thing that's harder to understand. But you gain stuff, right? What you really particularly gain is that this is a compact topological group. Okay, so finite groups are obviously compact topological groups. You take an inverse limit of compact things, it'll be compact still. So it's a compact topological group. And for a residually finite group, it'll contain a copy of gamma, a natural copy of gamma, as a dense subgroup. So you've sort of taken your discrete group, gamma, and you've compactified it, right? You've made it a dense subgroup in this compact topological group. And a key point is that this compact topological group will have exactly the same finite images as the group you started with. Okay, so you've taken this discrete group, you've manufactured it to be a dense subgroup of this compact topological group. So the compact topological group has exactly the same finite images. Now, I brushed over a key point there. I didn't use the word continuous for finite images. And I've used, and that's not part of the general nonsense. That's actually using a deep theorem of Nikolov and Siegel about, which relies on the finite classification of finite simple groups, for example, which says that every homomorphism from a finitely generated profinite group to a profinite group is continuous, in particular to finite groups. If you weren't worrying about that before, don't worry about it now. Okay, so the profinite completion is just a way of packaging up the finite quotients of a group. Now, you're not going to have to understand that for the remainder of this talk. And that's because of this very nice thing which was proved by, it appeared in various places in the 1980s, including Alex Lubotsky's thesis, which is for finitely generated groups, it follows from the universal property that if two groups have the same profinite completion, then they have the same finite images, right? Finite quotients. The non-trivial part of this proposition, this theorem, is that if finite generated groups have the same set of finite images, then they all fit together nicely to give an isomorphism of profinite completions, right? So when I'm talking about profinite completion, you you don't lose any content by reading statements like that, saying things have isomorphic profinite completions, as the more naive statement that things just have the same set of finite quotients. Okay? So you could read, whenever you see gamma hat, if you think of that as the set of finite images of your group, you don't lose anything. You genuinely have all the mathematical content in the setting of finite generated groups. Okay, so we're interested in profinite rigidity. So a finitely generated residually finite group is profinitely rigid in the absolute sense. If whenever you find something else which is finitely generated residually finite with the same set of finite images, they're forced to be isomorphic, right? That's an obvious rigidity theorem. They're equivalent in some weaker sense. They're forced to be the same, right? So I always like to say this. Gamma is a beautiful classical group that you've got. You want to understand. You hope it's so beautiful that it's unique. You find a group gamma lying in. You find a group lambda lying in the gutter, and this horrible, dirty group, which you know is residually finite for some reason. You test it, and it has all the same finite quotients as your group. That means when you clean it up, it really is going to be isomorphic to your classical group. Okay, so that's what profinite rigidity should mean. That your group is uniquely determined by. I just realized I forgot to start my clock. Does that mean I have an hour from now? Oh no, I don't. All right, so we're trying to prove theorems like that. That if two things got the same finite quotients, we're asking, are they going to be isomorphic? And obviously, in pursuing that, it'll be useful to identify profinite properties. The obvious definition that a property of groups is a profinite invariant if anything with the same profinite completion, if gamma has the property, then lambda has that property. Okay, that two things with the same profinite completion either have the property or not. Get rid of that typo quickly. Right. So let's think about some easy examples and ask ourselves whether they're profinitely rigid or not. So let's take the free abelian group of rank R. Is that profinitely rigid? Right. So you find some finite generated group. It's got the same finite images as z to the r. Is it actually z to the r? And the answer is yes. Okay. So I think this is the only proof in the talk, but it's worth doing this proof because it illustrates a useful point. So first of all, you've got this mystery group that's got the same finite images as z to the r. Step one, right? So, and this step is much harder in other contexts. This is often the hardest step. So I've just got this group that I found lying in the gutter. So in particular, I don't know if it's abelian or not. Right? So is it abelian? So you first need to think of a reason it's abelian. And the answer is yes, it has to be abelian, because suppose it wasn't abelian, so then you'd have some commutator which wasn't trivial, but then it's residually finite. So that commutator survives in some finite image, which means this mystery group would have a non-abelian finite image. But z to the r doesn't. So that would mean that the gamma, this mystery group, and z to the r would have different finite quotients. Okay? So that was step one. Instead of just a group you found lying in the gutter, you suddenly get yourself into a context where you have structure theorems. Now I know that gamma is a finitely generated abelian group, but I know what finitely generated abelian groups look like. Right? And therefore, it's easy to figure out that they all have different quotients. Okay? So you can figure out the rank, for example, and you see that gamma is indeed z to the r. Right? So there's that first step of a group that you found in the gutter, cleaning up a little bit to get into a nice context where you have structure, and then using what you know about groups in that setting to prove a rigidity theorem. And you can do that sort of thing, that same sort of argument, whenever you've got a group law. So if you do that with a nilpotent group of class C, for example, you find a mystery group with the same finite quotients. Well, you'll take some repeated commutator and run that argument again. You'll see this mystery group actually has to be nilpotent of class C. And then, so instead of asking if your given nilpotent group is that profinitely rigid amongst all groups, you only have to ask among nilpotent groups. But there, something interesting happens, and Higman, I think, was the first to realize this, that some non-abelian nilpotent groups are profinitely rigid and some are not. Okay? But then there's a nice theorem of Pickle, who's a student of Baumslag, and then this was improved upon by Grunewald and Siegel, this all in the 1970s. It's true that not all nilpotent groups are profinitely rigid. You can find different finitely generated nilpotent groups that have the same finite quotients. but you'll only be able to find finitely many. Right? So in any given genus, that is, if you ask which groups have the same finite quotients as a fixed one, you'll only ever get finitely many. Okay, that's the finite genus, profinite genus. Okay, so that, so that's good, right? Things are going quite well so far. Now things are about to go horribly wrong, right? So far you might think, oh, you find things in nature and they're profinitely rigid, but you only have to go a tiny finite step away from cyclic groups to find things which are not profinitely rigid. So this is in a paper Baumsager. He was sort of boiling down an idea of Serre from 10 years earlier. And look at these two groups. Well, they look remarkably the same, right? So you've got a normal subgroup, cyclic of order 25. And it's acted on by Z, right? So it's a semi-direct product of Z25 with Z. But the actions are different in the two cases. So in the first case, alpha is multiplication by 6. In the second case, beta, the action here, is multiplication by 11. 11 is 6 squared mod 25, you notice. This is actually, this has finite index in that, and that has finite index in that, abstractly. Now, though, you might wonder, since those groups are so similar, are they actually just isomorphic? So a little exercise proves that they're actually different, right? And the slightly harder exercise, but once you know it's true, you can really do it for yourself, prove that their finite quotients are all the same. Right, so those two groups there, very concrete groups, they're not isomorphic, but they have the same profinite completion. They have the same set of finite images. And that's about that's as small a step as you can get away from abelian. Those are two generator virtually cyclic groups. They're nilpotent of class 2, but they're not profinitely rigid. Okay, and now a more interesting example, that's already pretty interesting. A slightly larger example is coming from 3 manifolds. So if you take torus bundles over the circle with an Ossoff holonomy, so take 2 lattices in Sol. If you take different holonomies, if the action of Z on Z squared, it'll give you some element of GL2Z. If you take 2 elements which are not conjugate in GL2Z, you'll get different manifolds. Right? You get 2 different 3 manifolds, and their fundamental groups will be different. So take those 2 matrices. Okay. Those 2 matrices are not conjugate in GL2Z, but they are conjugate in GL2 of Z mod M for every M. Right? This is class field theory. This is to do with fractional ideals. They're conjugate in every finite image of GL2, but they're not conjugate in GL2. So because of that, it follows quite easily that you got these 2 different lattices in Sol, these 2 different 3-manifold groups. So they're not isomorphic, but if you look at a finite image, then the image of this will be finite, and so the action will factor through something like this. And so all of their finite images will be the same. So here's 2 3-manifold groups, which are not isomorphic, but they have the same finite images. Okay? So even in the nice setting of geometric 3-manifolds, you don't get profinite rigidity. Okay. But now something interesting happens if you move towards hyperbolic geometry. So that's about Sol, about solvable geometry in dimension 3. And so they were torus bundles over the circle. Now, if you puncture those tori, right, if you think of the corresponding punctured torus bundle over the circle, then the fundamental groups, instead of being Z squared, I haven't written this anywhere. Oh, yeah. Instead of being Z squared semi-direct product, they'll become a free group semi-direct product Z, right, with the same holonomy. When you puncture the torus bundles, so you get different fundamental groups, and in that case, you do get profinite rigidity. So 2 such groups, the fundamental groups of torus bundles over the circle, if they have the same profinite completion, then the groups are actually the same. Right? And in fact, those classes of groups are all profinitely rigid in the class of 3-manifold groups. That is to say, take any 3-manifold group with the same finite quotients as a punctured torus bundle over the circle, then that group will actually have to be the fundamental group for punctured torus bundle over the circle. And in fact, the manifolds will have to be homeomorphic. So let me say that again. So in Sol geometry, but you move towards hyperbolic geometry, and somehow the lack of rigidity goes away. which is a clue to other theorems we're going to be looking at. Yeah, no, that's a good question. Yeah, so this theorem is definitely for one puncture. Yeah, not. Yeah, there's things you can say with more punctures, but it's not as clean as that. It's not. We don't know that it's unique like that. Thank you. That's a good question. Okay, now so let me distinguish three types of profinite rigidity. So this is where we talk about three different types of profinite rigidity. Right, the absolute case, the hardest case, is you want to prove a group's profinite rigid, and that's where you're just dealing with groups in the gutter, right? So you've got the thing, your classical thing, say a hyperbolic manifold group, that's your gamma, and you say it's profinitely rigid in the absolute sense if whenever you find any finite generated group in the gutter, provided it's residually finite and it's got the same quotients as finite quotients as your group, it actually has to be isomorphic to your group. Okay, there's no fake guys out there. That's the absolute case. Now, proving theorems like that's going to be very hard unless you have a group law. We sort of did it for abelian groups because there was an easy argument that said the group you found in the gutter had to be abelian. But in other settings, you're going to have to prove a theorem that says the group you found in the gutter is actually one of a nice collection where you have a structure theory. Okay? So the first part of any theorem about absolute rigidity will be like in the abelian case, trying to maneuver yourself into a setting where you have structure. And then once you've got into a setting with structure, say you're in some nice class of groups gamma, then you only have to prove a relative theorem. So finite generated residually finite group in some nice class is profinitely rigid in that class among groups in G. If given anything in that class, then if you've got the same finite quotients, you're isomorphic. Okay? So those sort of theorems, they might be hard, they might be interesting, but they're going to be much easier than this because might have some structure theory. You might know what groups in this class G look like. Okay? So we distinguish between absolute profinite rigidity and profinite rigidity within some class of groups, relative. And then there's another setting where you're sort of given more of a head start than this, which is called Grothendieck rigidity, for a reason I'll explain, is that not only have you got groups in the same class, but you say a group gamma is Grothendieck rigid if you only have to distinguish it from its subgroups. Right? So a group is Grothendieck rigid if whenever you got the inclusion of a subgroup, that particular map should not be an the only way that the inclusion of that subgroup is an isomorphism is if actually that inclusion was already an isomorphism. Okay? So the subgroup P should be smaller, so it's this map from P hat to gamma hat shouldn't generally be an isomorphism. So you might wonder, can that happen in any non-trivial way? And that's what we're going to talk about. Okay, so everyone got that? So this is asking about all groups in the class. Here you're even just looking among the subgroups of gamma, and you're not asking, does there exist an isomorphism? You're asking whether one particular map is an isomorphism. So it's a weaker form of rigidity. So those are the three types of profinite rigidity that one talks about, that I'm going to talk about here. Oh gosh, okay. Right, okay. Right, now, so I'm going to start explaining some theorems quickly now, or stating some theorems at least. So is there anything interesting beyond sort of things that have a group law that are profinitely rigid? And this is what I'm going to describe now is work with Ben McReynolds, Alan Reed, and Ryan Spittler over the last few years. So a group is full-sized or grown up or proper or something, right, a real group, if it contains a non-abelian free group, right? And that's a convenient way of saying it's not something in a variety of groups. It's not an nilpotent group or solvable group, something like that. It doesn't have a group law. Okay, so are there any full-sized group? And the point about full size is that first step of going from a group in the gutter into some nice class. There's no obvious way to do that. Are there any full-size groups that are profinitely rigid in the absolute sense? That's the question we want to answer. And I wouldn't be talking about it if it wasn't something to say, of course. So a couple of years ago, we proved the answer is yes. In fact, there are arithmetic lattices in hyperbolic space in both dimension 2, lattices in dimension 3, the arithmetic lattices and PSL2C, so hyperbolic, three-dimensional hyperbolic manifolds and orbifolds. And in PSL2R, Fuchsian groups, groups that act on the hyperbolic plane, you can find arithmetic lattices in both those groups that are profinitely rigid in the absolute sense. They're profinitely rigid amongst all finitely generated residually finite groups. Okay, so everyone, that's everyone got that statement? It's sort of the simplest statement you could hope to make, that there do exist these absolutely profinitely rigid groups. Now, I'm not going to try and sketch the whole proof of that now by any means, but I just want to say that exists. Now, it's not just an existence, there's some very concrete things. That group there, for example. Right? If you have a finite generated residually finite group with the same images, finite images as that thing, that triangle group, that mystery group, when you clean it up, is actually isomorphic to that triangle group. Right? That 3, 3, 4 triangle group is profinitely rigid in the absolute sense. One might wonder why, and it's a long story. Okay, in examples in dimension 3, that Bianchi group, PSL2 of the Eisenstein integers, not the Eisenstein integers. No, PSL2 is there to join a primitive cube root of unity. That Bianchi group, that's profinitely rigid in the absolute sense. There's various other small hyperbolic manifolds. For example, the smallest hyperbolic manifold, the Weeks manifold, its fundamental group is profinitely rigid in the absolute sense. Okay. There's some separate arguments for each case. We only have finitely many examples of hyperbolic lattices which are profinitely rigid in the absolute sense for the moment. But it seems reasonable to conjecture, in fact, that all lattices in PSL2R and PSL2C are profinitely rigid. In particular, that incorporates this older question of Remes-Lennikov, which is still very much open. Are finitely generated free groups profinitely rigid? So you find a group in the gutter, finitely generated, residually finite, and it has the same images as a free group. So say it maps onto all 3 generator finite groups. Then is that mystery group the free group of rank 3 or not? We don't know that. Okay? There's progress on this question. We can say various things about the candidate groups, but it's still very much an open question. So those two conjectures sort of follow naturally from what I've been talking about. This last one is to get at the main theme of today's talk, which is the difference between finitely generated and finitely presented groups. Okay? And there's a big difference. And so here's a conjecture. Again, it's out of reach, not least because it would involve solving this conjecture. But I want to state this conjecture to highlight the difference between finitely presented and finitely generated groups. So take a direct product of 2 free groups, say a free group of rank 2, right? F2 cross F2. If you've got, I'm going to explain to you why that is not profinitely rigid amongst all finitely generated groups. Okay? So you can find finitely generated residually finite groups that are not isomorphic to 3 times 3, but have the same finite quotients as 3 times 3. But the groups I'm going to describe to you are finitely generated but not finitely presented. And the conjecture would be, I conjecture it to be, that in fact for finitely presented groups, that it is rigid. There's no finitely presented mystery group that has the same finite images as F cross F. Okay, now, it's not obvious to me why, a priori, why there should be a big difference between the worlds of finite generated and finite presentation, but there is. And that's what I want to try and move towards now. Okay? So what Alan and I have been working on with Ryan Spittler over the last couple of years, finished it in the fall, is this theorem. So we think F cross F is like this, but we can't prove that, it's a long way off. But we can construct finite presented, residually finite groups, and they're very concrete groups, which we'll tell you about, so that these groups, such a gamma, is profinitely rigid amongst all finitely presented groups, right? So you've got a finitely presented residually finite guy with the same finite quotients. Actually has to be isomorphic to this one. But you can find infinitely many non-isomorphic finitely generated ones with the same profinite completion as this. Okay? So you've got infinite profinite genus amongst finite generated groups, but none of the mystery ones are finitely presented. Right? They're all finite generated groups that are not finite presentable. And how are you going to prove such a theorem? Well, where are you going to find these groups? Well, actually, the way it goes is you first prove this, which is any finite generated group with the same profinite completion. You find it in the gutter. It's not related to the context in which your group lives. But you've got to somehow manufacture a map. And what you end up doing is you end up manufacturing an injective map from the mystery group to your classical group that induces the isomorphism of profinite completions. In other words, you're proving that this is a Grothendieck pair, that actually this group gamma fails Grothendieck rigidity amongst finitely generated groups. Okay, but only amongst finitely generated groups, not among finite presented groups. And these groups gamma, they're very concrete groups. It'll be the fundamental. Such gamma will be the fundamental group of a certain type of Seifert fibered space, a nice 3 manifold times another one. So these are Seifert fibered spaces. So yeah, here was talking about SL2R tilde geometry. So these are manifolds with SL2R tilde geometry. These are lattices and SL2R tilde. Take a direct product of two of those things. If they're Seifert fiber spaces where the base orbifold is a 3-3-4 triangle group, the 3-3-4 sphere. Is that statement clear? So that's the end of what I hope the natural questions and the main theorems. Okay, so that's the bit of the talk where it's also. If I did it right, there shouldn't be any mysterious there. The groups are concrete groups. The questions are concrete. The answers are concrete. Right? Now the technicalities start. Okay, why are these things true, and how might you go about proving it? And how are you going to prove that thing is a profinitely rigid group, for example? Well, what I'm not going to do, I might do some of this, is explain this very complicated process of given a group in the gutter, how do you get it into a nice context? Okay. I'm going to talk about this sort of last part. This last part of the thing. After you've got into this nice situation of taking the mystery group and putting it inside the classical group, how are you then going to tell that whether or not this inclusion is really an isomorphism? So this is about the study of Grothendieck pairs. So a pair of groups, an inclusion of a subgroup, is a Grothendieck pair if the big group is residually finite, the subgroup's a proper subgroup, and the inclusion map induces an isomorphism of profinite completion. So another way of saying that is that the image of P is dense in the profinite topology of, well, so it's saying more than that. So it's saying two things. It's saying that whenever you take a finite quotient of gamma, P will map onto that finite quotient, this subgroup, and those are all the finite images of P. P has no others. Okay? That's what that statement says. Now, here's two sort of meta examples, two ways in which you might try to manufacture Grothendieck pairs. Suppose for a minute, leave aside for a second how you might do this. Suppose you could find finite generated groups, N and gamma, and a group Q that has no finite images, and its second homology is 0. You might wonder, why is he talking about second homology? And I'll try and explain that in a minute, okay? But just assume that for a minute. I suppose you've got a short exact sequence like that, okay? So you've got gamma mapping onto Q. Q has no finite images, and then you've got this kernel of this map, N. Well, you might naively think, well, I'll just complete things. I'll put hats on everything, right? So you put hats on everything, and there'll be N hat goes to gamma hat goes to Q hat, but Q hat's trivial, so then that first map should be an isomorphism. Now, if somebody said that quickly, you might think, well, that's a proof, right? And it sort of is, except you're not really allowed to just go around and put hats on things, right? Life isn't that easy. But it has a reasonable chance of working, right? It's a natural place to look for examples, and there's going to be this technical condition that comes in. And in fact, it's a little theorem that if you can do that, then that really will be a Grothendieck pair. Right? You really can go put the hats on, and that map there will really become an isomorphism of profinite completions. And then there's a slight variation on that where you have, again, a short exact sequence like that where this group Q is the same. It's got no finite quotients, and you're going to make its H2 Q0. And instead of just taking the kernel of that map, you take the fiber product of that map. So you probably all know what a fiber product is, but I'm going to say it because they're going to play an important role here. Fiber product of a map, so it's the set of pairs in gamma cross gamma that have the same image in Q. Okay, so it's related to the kernel, but it's different. Right? You're taking pairs that have the same image in Q. And by the way, we will be once we know things like this work, we know how to manufacture groups that have no finite quotients. I wrote one down for you on the first slide. Right? That also happens to have the property that its second homology is 0. So we do know how to manufacture groups like this. Okay? So once we make these arguments work. So that's where we're going to get Grothendieck pairs from. Okay? Is these two meta examples. Okay? So it's a naive idea that actually turns into a proof. Now, why are these called Grothendieck pairs at all? Because in his penultimate paper, or his penultimate published paper in 1970, Grothendieck was asking about the existence of these Grothendieck pairs. Not that he called them that, of course. What he was interested in at the time was Tanaka duality for discrete groups. He wanted to reconstruct a group from its representation theory. And he proved this theorem, that if you've got a homomorphism of discrete group, of finite generated discrete groups, then the natural map that will induce on the representation theory over any commutative ring, that will be an equivalence of categories if and only if that map of discrete groups induces an isomorphism of profinite completions. Okay? So we're approximating representations by finite representations. And so then, of course, you want to know when this happens. When does a map of discrete groups induce an isomorphism of profinite completions? And he wasn't sure if that ever happened in any non-trivial way. And hence he asked this question: if you got finitely presented residually finite groups, and you got a map between them that induces an isomorphism of profinite completions, does that only happen in the most trivial way? Does that only happen when the map of discrete groups was already an isomorphism? Okay. And the answer to that question, so there were various sort of partial answers, and the final answer was by myself and Fritz Grunewald. And Fritz is the one who really got me. This is how I got interested in profinite completions from this work. The answer is no. So you can actually construct hyperbolic groups. You can make them matrix groups if you want. So finite presented groups, finite presented hyperbolic groups, take a direct product, then you can find subgroups, and they're called P because they're going to be fiber products. You can find finitely presented subgroups so that the subgroups are infinite index. It's not abstractly isomorphic to the big group, but the inclusion does induce an isomorphism of profinite completions. Okay? So there do exist finitely presented Grothendieck pairs. Remember, that's called a Grothendieck pair when you have such a subgroup. Okay, now I'm going to speed up now because this is technicalities, and so this is just to see quickly where these technical conditions arise. So let's go back to that meta example number 1, where we're trying to manufacture short exact sequences. So those are finitely generated. That's some group that when you put a hat on it becomes trivial. It's got no finite quotients. Where does this condition on H2 come from? So, like Anne was doing the other day, you take the Linden-Hochschild-Sayre spectral sequence associated with short exact sequence. If you look in the bottom left-hand corner of that spectral sequence, you'll extract a short exact sequence where the second homology, this is all with z coefficients, second homology of the quotient goes to the group of co-invariants of H1 of n, goes to the homology, which is just the abelianization of the group in the middle, goes to H1 of that. Okay? Just short exact sequence that falls out of the spectral sequence. Now, why am I interested in that? Well, so what is the group of co-invariants is you take that coefficient group, the homology of the n abelianized, and then you factor out the action of Q. But Q is a group that has no finite quotients. And if a group's got no finite quotients, it can't act on a finitely generated abelian group in any non-trivial way. That's more or less the fact that a finite generated linear group is residually finite. Right? If a group has no finite images, it can't act on an finite generated abelian group. So that action's trivial. So there's nothing to factor out. So in fact, because the Q has no finite quotients, that degenerates You just get a short exact sequence with h2 of q going to h1 of n going to h1 of gamma. Now, we're hoping that n and gamma have the same finite quotients, from which it follows that they have to have the same abelianization. So if they're going to have the same abelianization, that group is going to have to be, the image of that map is going to have to be 0. That's a necessary condition. Okay? And therefore, that's why you want to impose this condition on Q. And it really is a necessary condition, that you have to make that second homology group 0. Okay? So that's why that condition comes in. And then it's not hard from there to prove that that's enough. So if you've got a group with no finite quotients and its second homology is 0, then that meta idea just really works, and that's a way of constructing Grothendieck pairs. But you still got the problem that you have to come up with some short exact sequences that look like this. Right? Now, fortunately, there's a construction of RIPs using small cancellation theory from the 1970s that will give you lots of examples like that. So what RIPs will do is you give him any finitely presented group Q. So finitely presented means there's a nice map of a free group on, but he says, but there's also a nice map of a hyperbolic group onto Q. And the advantage of doing hyperbolic rather than free group is you can make the kernel finitely generated. Okay, so give RIPs any finitely presented group, he'll give you back a short exact sequence of a hyperbolic group mapping onto your favorite Q with finitely generated kernel. So if you plug in one of these suitable Q, that's a way of manufacturing Grothendieck pairs. Right? I should have said, so with modern technology, particularly due to Danny Wise, you can make sure that hyperbolic group is residually finite. So that's a way of manufacturing Grothendieck pairs, where you've got a finitely generated subgroup sitting inside a hyperbolic group. That kernel is finitely generated, but now it's not finitely presented. It is never finitely presented. Okay? So this is where you see the first time a real difference between finitely generated and finitely presented. This is a way of coming up with Grothendieck pairs where the big group is finitely presented, the subgroup is finitely generated, but not finitely presented. So in particular, it's telling us that being hyperbolic is not a profinite invariant. Here we've got two things, n, which is not hyperbolic, h, which is hyperbolic. They have the same profinite completion. They have the same finite images. I still don't know if you've got a finitely presented group with the same profinite completion as a hyperbolic group. Does that have to be hyperbolic? That's still open. Now, we mentioned fiber products as a way of souping up kernels. This is something you do to get away from the problem that when you're trying to manufacture short exact sequences to apply the first template to, it's kind of hard. Well, RIPs will do it for certain examples. You give him a Q, he'll manufacture an H so that you get a finite generated kernel. But when you're in applications, you don't want to do that. What you got is you've got some group which plays the role of H here that you want to prove is or is not profinitely rigid. You want to map it onto things, perhaps Qs like that, right? And then you're not going to be able to control the kernel, and particularly you're not going to be able to make the kernel finitely generated. And a way to get around that is to take fiber products. There's a very easy lemma that tells you without any control on the kernel, that's the 0 in the 0, 1, 2 lemma, you have no control on the kernel. As long as the group in the middle is finitely generated and the group on the right is finitely presented, the fiber product in H cross H will always be finitely generated. And then you can soup up this proposition that says making H2 of Q 0 is all you need to do. And this originates in a paper of Platinoff and Tavkin, this argument, and was extracted. Yeah, so I'll come to that in a minute. And the same thing works for fiber products. As long as Q's got no finite quotients and its second homology is 0, the inclusion of the fiber product will give you a Grothendieck pair. Okay? So now you have a better way, a more flexible way of making Grothendieck pairs. As I say, originates in the work of Platinoff and Tavkin, and then it was used by Bass and Lubotsky to solve a conjecture of Platinoff. But there's a worry here, I might say, is that these fiber products will be finitely generated, but they won't be finitely presented in general. You have to do something a bit harder. So this is Platinoff and Tavkin's work. This is how they proved that a direct product of two free groups is not Grothendieck rigid, right? So you take that group Q I was talking about before, just map a free group onto it, then the fiber product of that map will give you a subgroup of F cross Fs at the inclusion as a Grothendieck pair. Okay. Now the shortcoming is that fiber product is never finitely presented, and that's something you get around using some more homology of groups, something about finite classifying spaces and third homology here. And by combining all of the ideas I've used, including that stuff about higher homology, that's how Fritz Grunewald and I solved this Grothendieck problem. Okay, now, I've told you that story to sort of tell you what happened with Grothendieck rigidity and how it was settled, right? But now, if you remember, the way this started is we want to try and explain this theorem of myself and Alan and Ryan Spittler about these groups which are absolutely profinitely rigid amongst finite presented groups but not finite generated groups. We're going to reduce that to some question about Grothendieck pairs. Now, I've sort of given the ideas that were around when we started this project, and we want to adapt them, but there's various technicalities in how you adapt them. So in the next few minutes, next 3 minutes, I'm going to, 3 minutes and then 3 minutes on something else. Why was F cross F not enough to solve the Grothendieck problem for finitely presented groups? It's because the subgroups of F cross F, there's loads of finitely generated, interesting finitely generated subgroups of F cross F. Those fiber products we're constructing give loads of interesting examples. But there's no interesting examples of finitely presented subgroups. This is an old theorem of Baumsegg and Roseblade. The only finitely presented subgroups of a direct product of two free groups are the obvious ones. They're either free or they're virtually free times free. The obvious ones are the only finitely presented ones. Now, with quite a lot of work, you can extend that statement about free groups to direct products of surface groups and more generally Fuchsian groups. And in particular, you can prove that if you've got a finitely, you do get interesting finitely presented subgroups when you take more than three factors, more than two factors here, free groups or Fuchsian groups. But the finitely presented groups remain well behaved in the sense that they're all closed in the profinite topology. Okay, so you can't use them to manufacture Grothendieck pairs. So in particular, if you take that triangle group that we love, it's Grothendieck rigid amongst all finitely presented groups, but not all finitely generated groups. So it has finitely generated groups where the inclusions and isomorphism and profinite completion, but there's no finitely presented ones. And that's a crucial step, the first step somehow, to getting to this theorem, that instead of just talking about subgroups of direct products of the triangle group, you have to talk about subgroups of direct products of central extensions. But nevertheless, you can prove that the finitely presented residually finite group you get by taking a direct product of two of these Seifert fiber groups, that will be profinitely. It has Grothendieck pairs where the subgroup's finitely generated, but none where the subgroup's finitely presented. And that's where this difference between finite generation and finite presentation really manifests itself, and it goes back to this fact about Fuchsian groups. Okay, now there's some more technicalities, which I'm going to skip over, because I said I want to use the last 3 minutes for something else. So we want to sort of make that business of So what we still haven't done, so I've told you there's no bad finitely presented subgroups of G cross G, but I haven't explained why there are bad finitely generated ones. I've sort of indicated how you might do it. You want to construct these Grothendieck pairs. But in order to do that, you have to map the groups we're given onto groups that have no finite images, and you control the H2. You have to make H2 0. Now, mapping onto groups with no finite images turns out to be something that's by now well known. Given any hyperbolic group, you can manufacture infinite sequences of proper quotients so that all the quotients are finitely presented and have no finite quotients. That's something you can do using relative small cancellation theory. Okay, so constructing maps onto groups with no finite quotients is not so hard from a modern point of view. But it remains remarkably hard to control the homology of those. Right? I can't think of a good way of ensuring that those things have trivial second homology. You'd like to sort of do something like take the universal central extension of those things, but that messes you up for various reasons. So there is more homology you can do to get around that, and this is So I mentioned this paper of Bass and Lubotsky in which they proved the Platonov, got counterexamples to the Platonov conjecture. They had to get around a similar problem, and we have to do it here. And instead of just mapping the group you're given onto a sequence of nice groups with no finite quotients, you have to do it in stages. So you've got this group you care about, you have to map it onto the commutator subgroup of something else, which has to have finite index and something else, which maps onto something else. It's ugly, right? It's an ugly but useful theorem. Ugly but useful doesn't refer to the authors, it refers to the theorem. There's some variation on the naive idea that works, but you have to put intermediate steps in, and it means you need to put more constraints on the groups you work with. Okay. So I'm going to skip over that. The rough idea is that it might be ugly, but it really is useful that for Seifert fibered spaces over our base orbifolds, using various duality arguments, you can make it work. Right, so the last 3 minutes, which is now down to the last 2 minutes, I think, is it? 4 minutes. Oh, okay, that's fine. So that is the sketch. So you know, I hope I explained to you what the main problem is, trying to prove things are or are not profinitely rigid. And then we found rigid groups. We found there's this big difference between working with finite generated or finite presenter groups. I now want to go back to this question of finding profinite invariants. Now, what we didn't do in those theorems is we didn't characterize our groups by writing out a list of properties that turn out to be profinite invariants. And I'd like to spend this last couple of minutes just describing, using similar ideas about Grothendieck pairs, why all sorts of things that you might hope are profinite invariants aren't, right? So the idea is you might hope, for example, say somebody said to you, well, I think if you've got two groups of the same finite quotients, and one of them's got a z cubed subgroup, then so does the other one. That seems like a reasonable guess, right? Or if my favorite group's got cohomological dimension 2, and I've got a group with the same profinite completion, then the other group should have cohomological dimension 2. Right? They'll mumble something about Serre and goodness. Right? So the point of this theorem is to say that actually all sorts of things theorems like that often don't work, right? So here's the sort of the meta theorem. Given any finitely presented group gamma that's residually finite, one can construct a finitely generated, residually finite, free by free group. Okay, so it's a semi-direct product of an infinite free group by a finite generated one. So it's not right, but the whole group is finitely generated. So this action sort of is transitive enough here that it makes the group finitely generated. So there's a free by free group that includes into not your original group gamma, but you take your original group gamma, free product with a free group, that's harmless. Direct product with another free group, that seems quite harmless. But actually inside there, you can find a Grothendieck pair. So you can find a free by free group so that the inclusion induces an isomorphism of profinite completions. Now, that group gamma, you just get rid of that and you collapse that. That group gamma is obviously a retract of that group on the right. So it follows that the profinite completion of gamma hat is sitting inside the profinite completion of this free by free group as a retract, right? Which tells you that, well, that's weird. So in particular, if this is a group with large cohomological dimension, like z to the million, that says that the profinite completion of this free by free group has to have cohomological dimension at least 1 million. Right? So inside the profinite completion of a finite generated free by free group, you can find anything. Okay? And therefore, there's all sorts of things that can't be profinite invariants. For example, this tells you there's no non-trivial statement of the form. If you've got two profinitely isomorphic groups, and one of them has a subgroup H, then you can never assume that the other one has a subgroup H. Right? It just can't happen, because you could make one of those a free by free group, and then you're restricted just the subgroups of free by free groups, which are just free by free groups. So as I say, cohomological dimension is definitely not seen by the profinite completion, and it's been known since a very nice short paper of Alex Lubotsky about SL3Z that you can take a torsion free group and torsion can appear in the profinite completion. But this also shows it, right? Because this group gamma could contain every finite group, Now you have a two-dimensional group, a 3x3 group, whose profinite completion contains a copy of gamma. So it can contain every finite group. So torsion can just magically appear in the profinite completion of a group, even if the group is torsion-free. Okay? And then all sorts of other things can't be profinite properties, like being torsion-free, being locally indicable, left orderable, two-generator subgroups being finite presented, amenable subgroups, blah, blah, blah. So it's actually very hard to find profinite invariants, is the short thing, right? That things you think might be detectable in the finite quotients aren't, which sort of makes these profinite rigidity theorems more striking, right? Because it says you can't approach them via profinite invariants. You really sort of have to use global properties of the group. Okay. How do you prove that? Well, you do fiber product tricks again, but for that group Q, you need an asymmetric version, and you need something which I did a few years ago in this memorial volume for Baumslag. There's a variation on an old trick of Higman. You can construct a 4-generator finitely presented group, which is universal in the sense it contains every other finitely presented group. But you can make it so it's got no homology, and you can fiddle with it to make sure it's got no finite quotients. And you use that as the group Q in my meta construction. And you build fiber products over that. And that's how you prove this thing. Thank you.
Thanks, Martin. Do we have any questions for Martin? Yeah, here.
So what did you tell us something about 3 manifold groups in the end, or not? Are they?
Yeah, right. So I'll tell you something, but not enough. So there do exist these finite lists of hyperbolic 3 manifolds, which are profinite rigid in the absolute sense. There's a lot more groups. So, for example, the first paper Alan and I wrote on this about 3 manifolds was proving that, in particular, that the figure 8 knot complement is rigid amongst the class of 3 manifold groups. So it's distinct. And that's an example of this theorem with Wilton, that punctured torus bundles are distinguished from everything else by their finite quotients. But those are only relative theorems in the class of 3 manifold groups. There are then these sole examples that say certain things aren't profinitely rigid. There's a conjecture, which we can't prove, that all Kleinian groups are profinitely rigid in the absolute sense. There's a very nice theorem of Liu that says there's only finitely many Kleinian groups can have the same profinite completion. But that's a theorem within the world of Kleinian groups. It's not reaching outside it. Then there's a bunch of other theorems. For example, there's a nice construction of Hempel that's a variation on Baumslag's arguments that show that in H2 cross R manifolds, you can get examples of distinct things with the same profinite completion. So we know a lot, but we don't know nearly as much as we'd like to know.
You were looking at finite presented, rigid with respect to finite presented, but not finite generation. Is anything known about like higher finiteness, like F3, but not finitely presented?
So in general, so they won't be preserved by profinite isomorphism, because we're sort of seeing that the subgroups in Grothendieck pairs can have worse properties. I don't know nice positive theorems. In the sense, one could prove negative theorems where higher finiteness properties are not preserved. And these higher finiteness properties play an important role in these Grothendieck pair constructions, because they're really needed to in these 5 product constructions to get enough finiteness. But I don't know a nice positive result about higher finiteness properties.
So if a group is like Grothendieck rigid, then or like so it's weaker than the profinite rigidity, right?
It's a lot weaker.
But if you can, is there something else you can add that to it so that it would be profinite rigid?
No, that's where sort of the real sweat and tears come in. Is kind of trying to, in certain circumstances, and Alan's going to talk about this a bit. In certain circumstances, you try and take an abstract thing and force it it to be a subgroup. But I don't sort of have a machine for that. The only arguments of that sort which we have at the moment are very specific to specific classes of groups. There's no sort of machine that will work for large classes of groups.
And following your comment about the Kleinian group, is there any result showing close to like it being like Grothendieck rigid?
Oh, sorry, I should have said that. Yeah, for three manifold groups, we know they're all Grothendieck rigid.
Oh, okay.
Yeah, that's. I've forgotten who did the last step of that. Was it Sun? So Hongbin Sun, yeah, did the last step of that. But there's various partial results by different people along the way. Yeah, but so that's something we know about three manifold groups. They're all Grothendieck rigid. Yeah.
Any other questions?
When you look at the set of all possible finite quotients, you're also looking at the possible with the multiplicity, right? I mean,
well, that's a good point, and it's an interesting point. You'd think you'd have to count, but in fact, using a sort of Reith product construction, because you're looking at them all at once, you don't have to count them with multiplicity. It's a consequence that if you literally have this is only for finite generated groups. If you literally have the same set of finite images without counting multiplicity, then you're profinitely isomorphic. And in particular, that says you'll have the same number of surjections to each finite group as well. So the multiplicity comes for free, surprisingly. And that's because you look at all groups at once. You see, and so to get an idea of, so say you pick a group like A5, right? And so you might think, well, this guy's got one map to A5 and this guy's got two. But then the guy with two will have a map to A5 cross A5 that you don't see in the other one. And so because you look at all the finite images at once, you get the multiplicity for free.
I see. Thank you.
And there's one more thing I should have said about three manifolds, actually. It's a very nice theorem of Heiken, that within the setting of three manifolds, you do get profinite invariants. In particular, being fibered is a profinite invariant. That's